go back to what we were doing. So from last time, we saw this Cauchy criterion for series, right? It's just like the meaning of the partial sums being a Cauchy sequence. It's just that it is. You just take the meaning of being Cauchy sequence and you apply it to the sequence of partial sums, and you get this one over here, that a series converges if and only if, for an arbitrary epsilon, you can find an entry point in such a way that the tail, so whenever you have the sum of the tail for any number bigger than n, so that's why it starts in n plus 1, and ending whatever you want, right? That's the little n. If and only if the tail can be made as small as you want, right? Smaller than epsilon in this case. So we saw this last time, and as a consequence, we proved the divergence test. So today we're going to pick it from there and show more consequences, starting from our old friend, the comparison test, right? So let's write it down over here, new piece of paper. I'll leave the Cauchy criterion there because we're actually going to use it. So this is theorem 2.7.4, and this is the comparison test. And this is what it says. It says, assume that the series AN and BN, let's use K, AK and BK, satisfy that 0 is less than AK, less than or equal BK. In other words, it's a series of positive terms. Well, I mean, these are the sequences, but the corresponding series will have positive terms, and the A's are smaller than the B's. Good. Then the following happens. If the series of the B's converges, so if the larger one converges, then the smaller one converges. And the contrapositive of this one is that if the smaller one diverges, then that means that the larger one diverges too, right? That's our old friend, the comparison test. And just like I said, note that 2 is the contrapositive of 1, right? So it's enough to prove one of these two. The other one is equivalent, right? So this one is says A implies B, and this one says not B implies A, right? So it's enough to prove one of the two. Okay, so let's do it. Proof.
Professor, are their indexes all K's or all N's?
These are all K's. I should make my case more distinct. They're all K's, and I didn't write from where to where. That's the other thing. I didn't say from 1 to infinity, because it really doesn't matter, right? I mean, with the convergence or divergence of the series, it really doesn't matter where you started, right? So it doesn't matter where it starts, and we know it goes to infinity. So whenever I don't write anything, you're assuming that it goes to infinity, right? But if we wanted it to be precise, maybe, I mean, it really doesn't matter. We can add these, and just the observation that I was making a note right now is that you can start whatever you want, and the convergence or divergence will not be affected. And let me write that as a remark previous to the proof. Remark. Note that the series from this converges if and only if you started whatever you want at t, converges for any t greater than or equal 1. So it really doesn't matter, right? Of course, the value of the sum will be affected, right? If you have the entire series and it has a specific value, if you remove a few terms, the value will change, but the fact that it converges will not, right? You will still get something convergent. right? So that's the end of my remark. Okay, so let's go to the proof. So we're gonna assume that a BK converges. And what is the meaning of this? Well, according to the Cauchy criterion, so by Cauchy criterion, see, let's put it back right here, right? So we say that some series converges means that for every epsilon, we can make this happen. And I'm gonna rewrite it, okay? So here we go. By Cauchy criterion, if and only if the following happens. For every epsilon, there exists some entry point capital N such that for every little n bigger than capital N bigger than, little n bigger than m bigger than capital N, the following happens. The tail is less than epsilon. So bn plus 1 plus bn plus 2 dot 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 plus bn, all of that less than epsilon. All right? Okay. But, and see how easy the proof becomes. So what is it that we want to show? We want to show that the A's, the series of the A's is convergent, right? So we have to use this inequality at some point, right? And the fact that the terms are positive. So the first thing that you should notice is that we don't need absolute value bars here because all of these numbers are positive. So we're adding positive things. So we don't need the absolute value bars. We will get the same thing. So note that the following happens. If I look at the same tail but with A's, so if I write an plus 1 plus an plus 2 dot dot dot, and I stop at n, like I said, because these terms are positive, we can disregard the absolute value bars and write it without absolute value bars. So this is going to be an plus 1 plus an plus 2 dot 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 an, right? Now I can use my inequality. So this one is less than or equal the corresponding b's, because every A is smaller than the corresponding B. Okay. Now we also said that this is because they're all positive. You can go back and put the absolute value bars if you want. That's okay. Okay. But then look at what we know. We know that this is less than epsilon. We have it right here. So this is less than epsilon. Okay. So what's the end? Well, the end is that this is what we did. We for any given epsilon, we can find a capital N. It happens to be the same capital N that works for the B's. That same capital N has the same effect for the A's, because look, when we add up the A's, we can forget about the absolute value, and term by term, those are smaller than the B's, and we know that the sum of the B's is less than epsilon. Therefore, the sum of the A's is less than epsilon, right? And that is precisely the Cauchy criterion. So now we use the Cauchy criterion going back. So this is if and only if, again by Cauchy criterion, if and only if the series of the A's converges. And we are done, right? Very, very straightforward proof. One of the easiest that we've seen, if you ask me, because all we are using is the Cauchy criterion and the inequality that we were given. There's nothing else there. All right. Okay. Questions? Okay. The next one is also one that we know is 2.7.6, and it's called the absolute convergence test. You may remember that from your calculus days as well. So let's write it here. Theorem 2.7.6, the absolute convergence test. And this is now considering terms that series that have positive or negative terms. We don't know. And what it says is that if the series of the absolute value converges, then the one without absolute value converges as well. So this is convenient, right? So the way we used it in calculus is if I gave you a series that you didn't know that had positive and negative terms, you could always try it out with absolute value and see if you could make that be convergent. And if that one is convergent, then this one is convergent. All right. Now, the downside, the sad part of this test is that it doesn't work the other way, right? So if this one diverges, you cannot say that the other one diverges as well, right? So maybe before we do the proof, let's write down that little remark. However, actually, let me wait for the remark because the remark ties it with the next one, okay? So let me wait on the remark. Let's proceed with the proof. How do we prove this one? And again, our workhorse here is going to be the Cauchy's criterion. All right, so let's do it. Proof. So we're assuming this one is convergent. So assume this series converges. What is the meaning of this by Cauchy criterion? So this is again Cauchy's criterion. It means the following: for every epsilon, there is some capital N entry point such that for every little n bigger than m bigger than capital N, the following happens. The tail of this is less than epsilon, and the tail looks like this: is am plus 1 plus am plus 2 dot 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 plus an inside all of that absolute value bars less than epsilon. Now, first thing you would notice is that I don't need the outside absolute value bars because I'm adding a bunch of positive things, right? So that's going to be relevant in just a moment. Okay, so let's now think about what we want. We want to find out something equivalent, but without the absolute value bars, right? If we can find the same thing, but without the absolute value bars, we would be set. And lo and behold, that's exactly what we can do. And it's very simple. So again, I'm going to write it in the same way as the previous one. I'm just going to say here, note that the one we want, which would be like this. What do we know about this one by the triangle inequality? Well, what we know is that the absolute value of a sum is less than or equal the sum of the absolute values. So this is am plus 1 plus am plus 2 plus dot 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 all the way to this guy over here. But that's the same as with absolute value, like I said before, because all of these terms are positive. We can, if we wanted to, put another absolute value bar outside. That's fine. And then by the assumption that we have, we know that if little n and little m are indeed bigger than capital N, then this expression is actually less than epsilon, right? And that's it, right? Again, we are done. So what is it that we did? We found, for a given epsilon, we found a capital N that, again, happened to be the exact same capital N that worked for this series. So that capital N had this property, and it's a good thing that what we want is even smaller than the one we know. So what we want is smaller than the one we know. The one we know is less than epsilon. Therefore, the one we want is less than epsilon. And we are done, right? So by the triangle inequality, this is less than epsilon. Therefore, again, by using the Cauchy criterion backwards, by the Cauchy criterion, so in this direction, right? By the Cauchy criterion, we get that this one converges, right? And And that's the end of the proof. All right. Easy, right? And again, it tells you how powerful is this Cauchy criterion. It really is just a matter of writing down the meaning of what you want, and it gives it to you right away. Good. So before I talk about the remark, let me write the next one. This next one, and we're not going to prove here. It's one of your, it's homework problem number 1 in 2.7. But it's one that you're familiar with as well. It's called the alternating series test. You've seen this one before in calculus, and this is what it says. We have a sequence, a sequence that is decreasing. So satisfies that A1 is greater than or equal A2, greater than or equal A3, etc. So it goes down, and 2, the limit of the terms is 0. If you have a sequence that satisfies these 2 properties, then if you create the one that alternates signs, so from 1 to infinity, -1 to the n plus 1, an, then this one converges. Right? So if you alternate signs, and every time you take things that are smaller and smaller, then it converges. Okay? And there's lots of ways of proving this one. So I think exercise 2.7.1 actually outlines 3 different ways of doing it. 3 different ways of proving this result in 2.7.1, right? So the proof is exercise 2.7.1. And actually any one of the 3 parts will give you a proof. Okay, but from this one, we can already give an example of why the previous one, the absolute convergence test, is not an if and only if statement. The converse is false. Because, so little example here, we can use the sequence an equals 1 over n, right? Of course, this one is decreasing, so clearly 1 is bigger than 1/2, which is bigger than 1/3, which is bigger than 1/4, etc. And also clearly, the limit of 1 over n is 0, right? It was probably one of the first examples we did when we started talking about sequences. So we satisfy these 2 properties. Therefore, the alternating series converges. And we know that already. We saw that in calculus several times. It's called the alternating harmonic series. So thus, this guy over here, -1 to the n plus 1, 1 over n, from 1 to infinity, which is actually 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, etc. This one converges. Right? And if you remember your calculus days, you may even know what it converges to, right? Anyone remembers? What is this equal to?
I squared over 6?
No, that's the 1 over n square, right?
Yeah,
That's the 1 over n square. And I doubt you prove that in calculus, because that's a hard proof. Beautiful result. No, this one is, it comes from the power series of log, if you remember that one. And it's actually ln of 2. ln of 2, man, that's a weird answer, right? It's ln of 2. I mean, we're not going to do that in this class to show why is ln of 2. But it is ln of 2. And what you should remember, though, is that at the beginning of this chapter, we talked about, I show you that weird things can happen if you put the same things, the same terms in a different order. I don't know if you remember that one. So we started with this one, with this exact one, and I did something to it. I divided it by 2, and then I added it with itself in a different way, and I got a different answer. but it had the same terms. They were just rearranged. Okay, and that was weird. We thought like, man, why is this happening? I mean, this is like adding the same things, only we have positives and negatives, and we get a different answer. And at the end of today's, we'll actually say why that happens. Hopefully, if we have the time. All right. So this one is convergent. However, if we don't have the alternating signs, so however, this one over here, we know it diverges, right? We saw that as an example as well. And now we could do it with Cauchy's condensation test if you want. You can check that this one diverges, right? So this one diverges, that one converges. And that one, I'm sorry, and this one is the absolute value of this one. So it's not true that if the one with absolute value diverges, the other one diverges. That's false. This would be a counterexample, right? So, and you should know this also from your calculus classes. So therefore, we can define absolute convergence and conditional convergence. So I'm just going to write it here. So we say that if a series that has absolute value converges, we say that the regular series converges absolutely. That's the new term we're learning. Converges absolutely. And if that doesn't happen, if the one with absolute value diverges, but the one without absolute value converges, we say that the one without absolute values converges conditionally. Right, and you know these terms. We see them in our 150B class. So what we're saying here is that this one over here, the 1 over n, then I mean the negative 1 to the n plus 1, 1 over n, the alternating harmonic series converges conditionally. Thus, this guy over here, negative 1 to the n plus 1, 1 over n, converges conditionally. But if you do others, like if we instead of n, we make it n squared, or if we make it 2 to the n, those are absolute convergent. Okay, so let's continue over here. So however, things like this, negative 1 to the n plus 1, 1 over n squared, from 1 to infinity, or if you use a power, say like 1 over 2 to the n, these guys over here are absolutely convergent.
Professor, when you can you just put the page on top down just a little?
Sure.
Thank you.
And the reason these are absolutely convergent is forget about the alternating signs and do them. This one would be 1 over n squared, which we have done before. It converges to pi squared over 6, someone said already. And this one converges because it's a geometric series. And we know that geometric series are convergent as long as the number you have here, in this case is 1/2, is less than 1 in absolute value. So that's why these two are convergent, right? So this is an example we did before, or by P series, because now we know the P series, and this one is by a geometric series, and that's the reason it works. All right, so good. So the last thing we want to do today, it's the more challenging one actually, and is to talk about this rearranging business, right? So we rearranged at the beginning conditionally convergent series. We rearranged negative 1 over the alternating harmonic series. So let me, I don't think I have, I would like to bring that up again, but let me see if we can do that relatively quickly. So
Professor.
yeah.
It's pretty interesting how like they converge even though the signs alternate. Like I can't like picture it in my head.
Oh, there's an actually. Okay, let me make a picture that will probably convince you why. It's part of the proof of the alternating series test. So you're gonna do it on your own in this exercise. But look at what we're doing here. See, let's try to do a picture of what's happening here. So here's the real line, yes? And you start with A1, right? So in this series, the first thing you do is you add A1. So here's 0, right? And then you're jumping A1 units this way, A1, right? This is a jump, a positive jump, because A1 is positive, right? Of length A1, yes? And then what's the next step? The next step is, in the series, is you first do A1, then you do minus A2. So now you're gonna jump backwards, and that jump backwards, what you know is that it's smaller than A1. That's important, right? So you're gonna jump backwards, but when you go backwards, you're not gonna go past 0. You're gonna go backwards like this. See, this is A2. So you go A1 minus A2. Then you go again positive A3, right? And A3 is smaller than A2. So you're not gonna cross like this. That would be wrong, because that would be too big. The next one is smaller than A2, so it's gonna go like this, right? And then after that, so that's A3. And then after that, you go back smaller, and then you go forward even smaller, and then you go back smaller. And then doesn't this suggest to you that this should be convergent?
Yeah.
Right? Yeah, that's essentially the idea of the proof. You can, from this little diagram, extract the monotone subsequences that will give you the result, right? And so it goes like this. It alternates, right? Going high, and then low, high, low, high, low, high, low, but it's sort of circling towards a point, right? And that's the reason it's going to be convergent. So I'm providing you this explanation so that it just as to say that it's not that surprising, right? Once you see this, it's like, oh, of course,
Yeah,
this would be convergent. Yeah.
That drawing makes a lot of sense.
Yeah.
Thank you.
You're welcome. But let me go back to the other one. So the little trick that we did, right? So to show that things cannot be the same when you rearrange them. So let me recall that. I think we're going to have the time. You still have half an hour, and we only have one more result to do. So let's see if we could do that. So let's recall that little example that we did, right? So we started with the alternating series, so 1 minus 1/2, right? And we know that one is ln2 now, but it really doesn't matter. We called it S, right? So this is actually ln2. But you don't mind that, right? This is 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus 1/8 minus 1/10, etc. All right, so that one. And we did half of it. So what is 1/2 of S? Well, that's 1/2 minus 1/4 plus 1/6 minus 1/8. And this part is correct because we proved that property, right? If you multiply a convergent sequence, I skipped a term here, right? What did I do? This is 7 and this is 8. So this should be 14 and this should be 16. And it continues. Yeah, so this part is correct. We know that if a series converges and we multiply each of the terms by a constant, then the corresponding new series converges. So no problem there. The problem is when we do this, when we now arrange them this way. So let's, I'm going to repeat this. I'm going to put the 1/2 S as only in arranged in a different with spaces. So it's going to be space, then 1/2, space, negative 1/4, space, 1/6, space, negative 1/8, space, positive 1/10. And then on the bottom, I'm going to put S, the original one. So this is 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus 1/7 minus 1/8 plus 1/9 minus 1/10, etc. Right? Keeps going. And the other one also keeps going. So negative 1/12 is over here. And let's, since I positive, and then negative, right? Then add them like this, the way they are. And what do you get? Well, if we could add them the way they are, then we should get a half an s plus s, and that's 3/2 of s, right? And what should this be equal to? Well, this should be 1. This cancels, right? So 0. Then 1/3. Then this one is negative 1/2, right? Then 1/5. Then this one cancels, right? Then it's 1/7. And then this is negative 1/4. This is 1/9. This is negative 1/5. This is 1/11. And this is, there's something wrong with the signs. Let's see. Plus, minus, plus, minus, plus, minus. Should have
That should
gone.
be 0, not 1/5. Yeah.
Thank you. Yes, that was my, exactly. Something looked odd. Thank you. And then this is negative 1/6. And it continues like that, right? And then, okay, so look at the terms we got. So this is a different type of, so it's a series that uses the same terms, right? Observe. So here's the 1. Here's the negative 1/2. Here's the 1/3. Here's the negative 1/4 is further ahead. Here's 1/5. The negative 1/6 is all the way over here. Here's 1/7. The negative 1/8, you don't see it, but it's farther away. All right, it will appear. It's only going to be farther away. And then here's the 1/9. And then the negative 1/10, it will be even further away, but it will appear, and so on. So the terms here, the terms are exactly the same with the same sign. All right, so 1/3 is positive in here, and it's also positive in the original one, right? And 1/7 is positive and here and also here. So they have the same terms. So this series has the same terms as 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, etc., but in different order. But in a different order, right? And by having that, it turns out that the answer cannot be, see, it's impossible that the answer is the same, because then it would mean that 3/2 of s equals s, right? It would mean that s is 0, and s is not 0. Is definitely not equal to 0, the answer to this series, right? So however, so that's the important part here. However, 3/2 of s is not the same as s. So something is wrong here, right? Something is wrong here. And the part that is wrong is that this series over here, it is convergent, by the way, it is convergent, but the answer is not 3/2 of s. So this little trick that we did over here is wrong. You cannot do this trick with infinite series. You cannot rearrange them and expect to get the same answer. Okay, that's what this is telling us. When we rearrange them, we don't get the same answer. And in fact, we don't do this in this class, but it's a beautiful result that I can tell you. If you have a conditionally convergent series, like this one over here, you can rearrange it in a way that it converges to whatever you want, right? So you tell me what you wanted it to be the answer. I mean, you wanted the answer to be pi. We can rearrange it so that the answer is pi. You want the answer to be 34. We can make it so that the answer is 34. Whatever number you tell me, I can rearrange it to make it so that that's the answer. Isn't that incredible? I can also rearrange it so that it's divergent, by the way. I can rearrange it in a way that diverges. I can also do that. And that, it's like a mind explosion, right? I mean, it's something that you think should be true and it's not true. We're rearranging, you were just adding in a different order, and that makes it so that we don't get the same answer, okay? So now that's going for the crazy stuff. Now going for the sane, bringing it back to our sanity, here, it turns out that if you have something that is absolutely convergent, then it's okay to rearrange. If it's absolutely convergent and you rearrange it, you get the same answer. So some normalcy at least. Okay, so let's first define what we mean by a rearranging. So here's definition 2.7.9. And this, it says the following: let AK from 1 to infinity be a series. A series BK from 1 to infinity is called a rearrangement. A rearrangement of the original series if there is a bijective function f from the natural numbers to the natural numbers such that b sub f of k equals f sub a sub k for all k. Right? In other words, it's a rearrangement if we can change the subindices in a different way, right? But it has to be a bijection. It's not okay to put the same term twice or to avoid some of the terms that were in the original series, right? We want to keep all the terms and that each one of them appears exactly once. Okay, maybe we'll, I think we have time to put a little example. Let's write an example here. So example of a rearrangement. Example. Okay, so what about if we have a series? So let's say that our function f of k is the following. F of k is, let's make it so that, what do we want to do? Let's make the even ones go to the odds and the odds go to the evens, right? So I'm gonna make f of k be k plus 1 if k is odd. Right, so the 1 will go to 2 and the 3 will go to 4, right? And then if it's even, so I mean let's write down what we're doing here. So here's 1, 3, 5, 7, 9. So 1 I'm sending to 2, 3 I'm sending to 4, 5 I'm sending to 6, 7 to 8, 9 to 10, etc. And then the other ones, 2, 4, 6, 8, etc. Well, I gotta pick up the other ones, right? So they have to go to the other ones, and I have to not miss any. So I'm gonna send them to 1 less. So to k minus 1 if k is even. That's my function, right? And I'm illustrating it here in this right here on the side, what's happening, right? So so this is my new sequence. So what is the new series? So then the new series b sub k, remember that b, so what is b sub k? Well, that's b1 plus b2 plus b3, etc., right? And what is b1? Well, b1 is going to be a2 because look at the definition, right? So what is b of f of 1? B of, I mean, f of 2, right? So over here, b of f of 2, if I plug 2 in here, b of f of 2 is supposed to be a2, right? So
just on that, Professor, you put 8 goes to 9, but 8 should go to 7.
thank you. All right, and then, okay, let's go back here. So I want to know what is b of 1, right? What is B1? Well, B1 is A of, so what function goes to 1, right? That's, I mean, I kind of need like the inverse to figure it out, right? So what is the function? This is the function f. So f maps these numbers to these numbers. Which one went to 1? 2, right? So B1 is A2, right? Because f of 2 is 1, right? 2 went to 1. So that's why B1 is A2. So this is how the series looks like, but when you rewrite it, this is what we're doing. It's A2 plus A1 plus A4 plus A3 plus A6 plus A5 plus A8 plus A7, right? And so on. That's the series. And you can tell what we did. The only thing I did is I switched the order of these guys, right? Before it was first 1 and then 2, and I flipped them. And then it was first 3 and then 4, and I flipped them. That's all I did. So it's a rearranging. It's the same numbers. I just changed the order. And I didn't change it a lot with this example, right? I just changed it a little bit so you could appreciate what this, where the function comes in. All right? Okay, and now here's the result. Be the last result of this section. And it's theorem 2.7.10. And it says the following. It says, if a series converges absolutely, then any rearrangement of this series converges to the same limit. So if it's absolutely convergent, we're good. We can add the thing in whichever order we want.
Professor,
and we're gonna get the correct answer. Yes.
would it be given like, oh, this series converges absolutely, or is there something we can do to see if it converges absolutely?
Well, you can try to, you put absolute value bars and you try to see if it converges, right? And to do that, you can use any of the other tests for positive things. You can use the P-series test. You can use the Cauchy's condensation theorem. You can use the comparison test, any of them, right? That's how you would do it. Now, sometimes none of them work, right? There are very difficult series that you apply all of those series, all of those tests, and you still can't know. But okay, if you knew it was absolutely convergent, then you can add it, then you can rearrange it if you want to, right? You can change the order and it will still work. Okay? That's what this theorem says. Good. So that's let's do the proof. And that will be all that we need to do today. Okay. So our assumption, we're going to call it A, is that we have a series that is absolutely convergent. So assume the series AK from 1 to infinity converges absolutely to capital A. And then we need to consider a rearrangement. So let's call the rearrangement B. So let B of B sub K, the series of B sub K, be a rearrangement of the series of AKs. And we're going to need the partial sums of both of these series. So let's write them down. And set Sn will be the partial sum from k equals 1 to n of AK. And Tm, we're using different indices so that we avoid confusion, is the same one with the B's. All right? So that's, I haven't done anything. I just wrote down my assumption that this one converges absolutely and that we have a rearrangement. We need to show that this one converges too, and we need to show that it converges to the same limit. let's write down what it means for this series to be convergent to A first, right? And remember, for this series to be convergent, it means that the partial sums, these guys over here, are convergent to A. So then the sequence of partial sums converges to A. And what is the meaning of that? It means that if I pick an epsilon, so let epsilon greater than 0 be arbitrary. And I'm, again, as is common, I'm going to use epsilon over 2. And then we know that there is some entry number, n1, a natural number, such that if n is bigger than n1, then the partial sum Sn minus A is less than epsilon over 2. Okay? I haven't done anything yet either, right? This is just the definition of this series being convergent to A. Okay. Now, another one that I'm going to need is the absolute convergence, right? We need to use the absolute convergence. So I'm going to now use the absolute convergence with the Cauchy's criterion, all right? So by Cauchy's criterion, the fact that this series converges absolutely, then there is some entry number n2 such that the following happens. The little tail, so if little n is bigger than little m, which is bigger than n2, then the tail, which is a n plus 1 plus a n plus 2 dot 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 plus a n is smaller than epsilon over 2, right? And you'll notice that I left a little space here. And the reason I'm leaving a little space there is because I'm going to write it like this. I'm going to write it like the sum of AK. I'm going to use the sigma notation here. It's what I meant, from n plus 1 to n. Okay. And, oh, but I'm not doing it right because I said converges absolutely, right? So when we say converges absolutely, I should have actually done the absolute value bars of these guys, right? So this is really the one I mean, the one where you add up the absolute values, right? That's the one we need. So it's the sum of the absolute values. And you don't need the another absolute value bar outside of the entire sum because this is positive, okay? All right, so these are my assumptions. So I just, I'm using this one and as the fact that my series converges to A, and this one as the fact that my series converges absolutely. So the tails are smaller than epsilon over 2. All right, so now, now it comes the time to involve the B's, the rearranging. How are we gonna do that? How are we going to, you know, because we don't know anything about the function f, right? The function f could be weird. I mean, it could be something as easy as the one we did here, where we're just exchanging 2, but it could be something crazy, you know, like we send 1 to 2020, and then 2 to 17, and then 3 to, right, whatever. Any bijection can work. As long as it's a bijective function, it should work. So comes the time to involve the B's. So to do that, first, we're going to choose something bigger than these two. So as is common here, we're going to pick capital N to be the maximum of N1 and N2. Okay? And here's the thing. What we do know is that the function f, the rearranging, is a bijection. So there must be, if we take a look at the B's, so if we take a look at the B's, if I go far away in this series, eventually I should include whatever A's you tell me, right? So for example, you want to include A2, A7, and A14, 2, 7, and 14. So I just keep adding terms, right? I keep adding and adding and adding and adding and adding till I have in my terms A2, A7, and A14. And that should happen at some point because it's a bijection, right? There is some B that is equal to A2, and there is another B that is equal to A7, and another B that is equal to A14. So if I go to the larger of those B's, I will have the three of them, A2, A7, and A14 in the sum. So that's what we need to do here. So I'm going to write it here. Because F is a bijection, in fact, I'm using here the fact that it's onto, but I'm just going to write it's a bijection. We know that there is a partial sum of the B's that includes A1, A2, all the way to A sub capital N, right? And if you want to be precise and actually find out which one it is, here's how you can do it. You can choose capital M to be the largest of these numbers, the largest of the F of K between 1 and N. And this exactly tells you how far you need to go, right? You need to go as far away as M, because that number will be bigger than all the F sub Ks. So you will have included F of 1, F of 2, F of 3, F of N, and those are exactly the numbers that are equal to A1, A2, A3, all the way to AN. Okay, so then we're almost done here. 5 minutes to go. So here's what happens. If little m is bigger than capital M, if you pick something even bigger, here's what I want to compare. I want to compare the partial sum Tm, that's the B's, minus the partial sum S sub capital N. Right? Let's write it down. What is this? Well, this is the B's from 1 to capital M. And these are the A's from 1 to capital N. Right? But now remember what we said, the way we picked the capital M. We picked the capital M in a way that all of these numbers here, all the numbers A1, A2, all the way to AN, all of them are included in this sum. And of course, there's more stuff here. So this one is bigger. This one has more stuff. It has all the elements in here and then more other stuff. So this is actually the same as, if you think about it, so this is, all of these terms are included in here. Let me just make a little note here. So all of these appear in here. All of them. All right. So then if I apply the triangle inequality, so once I cancel all of these and with the ones that are on the other side, what I'm going to get is something like this. This will be less than or equal than, so what is this? I'll write it like this. Is the sigma. Oh, so these are the ones that survive. So the ones that survive are, I wrote all of these. So I'm applying the triangle inequality here. And BK is not A1 or A2 or AN. It's none of these, all right? Because all of these guys were canceled, right? And then if you think about it, this is less than if I do the AKs starting at N plus 1 and going somewhere, going see, that's another difficulty. I don't want to make it more complicated than it is. So going as far as what? Well, I don't know. The largest of the B's, right? These B's are equal to A's. And in this partial sum of B's, there must be one that is the largest one, the largest index of the A's. That's what I'm going to put here. So it's goes to some T or R. It doesn't really matter. Why doesn't it matter? Well, it doesn't matter because this number is bigger than N, and it doesn't matter because we wrote over here that the tail, right here, the tail is smaller than epsilon over 2. And for the tail, you don't care what this number is here on top, right? This number on top could be whatever you want, right? As long as it's bigger than the one in the bottom. So that's what we have over here. We have a tail of numbers like this, where this one is bigger than this, and the important thing is that this is less than epsilon over 2, right? And now for the final step, what I really want to compare is TM with A, right? So I have like 30 seconds to go. Here we go. So what we really want is what is TM minus A. Well, I use as my intermediary Sn, the partial sums of the A's. Triangle inequality. Break this into two separate ones. And this one we just learned is less than epsilon over 2. And this one, at the very beginning of the proof, we knew that Sn converges to A, so we made this one smaller than epsilon over 2. So this is epsilon, and we are done. So as long as you pick little m bigger than capital M, this happens. The sequence of partial sums of the T's minus A is less than epsilon, right? Thus, the TMs as a sequence approach A, that is the series from 1 to infinity converges, and it converges to A.